So let's start lecture 6, where we're going to transition to torsional members. So far we've been focusing on axially loaded members in chapter 4 and in the book. This is chapter 5, talking about torsional members. And there's a lot of similarities between a torsional member and an axially loaded member. And we'll talk about those similarities, and I think it'll help with your analysis because you can really duplicate a lot of the steps, and there's some shortcuts you can take that apply to axial members as well too. So the first thing that we're going to talk about is just what happens to the geometry of a prismatic circular shaft when it's subjected to torsion. Now we're going to go through this relatively quickly. There is a video on YouTube that goes through this derivation in more detail, but let's just talk about it generally. It's a similar discussion that we had with axial members as well too, but here we're focusing on a moment acting about the longitudinal axis of a member, whereas with axial members we were talking about an internal normal force that acts parallel to that axis, not a moment that acted about the axis. So here we're still focusing on the longitudinal axis, but instead of a force, we're talking about a moment acting about that axis. So if we started out with a prismatic circular shaft, we could draw cross-sectional lines that are basically circles. You can kind of see them on the perimeter of the circular shaft, and then we have longitudinal lines on the surface, and those are all acting or directed parallel to the longitudinal axis. If we apply a torque, those cross-sectional circles don't change shape, they simply rotate. They don't deform at all, they don't move in and out of the page whatsoever. All they do is they rotate, but they still remain circles. Now those longitudinal lines, they become twisted, and the angle of twist is something that we'll have to calculate of one cross-section relative to the other, because what's happening is that, let's say at the back of this shaft, I might start with, let's say I painted on the back on the circle like a vertical line going upwards. On the front, I could also have started out with a vertical line, but as I apply a torque to it, those two lines are now going to be at angles, or a relative rotation relative to each other. So radial lines remain straight, which are simply the lines from the center of the cross-section out to the surface. They'll remain straight, but they will rotate as we apply a torque to this cross-section. And whereas with axial members we found that applying an internal normal force caused a normal strain and a normal stress, here a torsional internal moment on the cross-section is going to induce a shear strain, and as a result a shear stress as well too. And the easiest way to discover that is, here's like a rubber tube that somebody painted a square on, a rectangle on, while it was unstressed. And then if you twist that tubing, that square becomes a rhombus or a parallelogram. Right? The angle of each of the corners of what used to be originally square are now non-square, non-90 degrees. And so this is the quintessential shear strain behavior that we talked about back in chapter 2. So we can already tell that torsion is going to cause some sort of shear strain, some sort of shear stress. And the big goal is going to be, well, how do we calculate that shear strain? How do we calculate that shear stress? All right, so your book goes through the derivation. I go through it in a separate video that you can look at on your own time. But we're just going to walk through it briefly. And the big goal here is trying to relate a couple different things. So the angle of twist is the relative amount of rotation of one cross-section relative to another. How much do they rotate about the longitudinal axis relative to each other? That's one part of this. But the other part of this too is also trying to find the shear strain, which is not exactly the same thing as the angle of twist. So they're both angle measurements, but we need to look at a little bit more detailed of a diagram to try to figure out how does the angle of twist relate to the shear strain. And so looking at this very closely, zoomed in a bit, the angle of twist is measured relative to the center of the cross section. That angle right there is our angle of twist. Just between two adjacent sections right here, it says delta phi. That's the angle of twist between two sections some differential length apart. And we're trying to relate that to the shear strain, which is represented up here as gamma. And like I said, the derivation is in a separate video, but trying to relate phi to gamma, we get this relationship over here from the derivation that the shear strain is equal to rho, which is simply the distance from the center of the cross section times d phi dx. All right, so that is the shear strain acting on a differential slice of this shaft, and it's proportional to the distance from the center of the cross section. Okay, some things to keep in mind, that the amount of shear strain for a cross section here, if this is the center of the cross section, the shear strain at the very center of that cross section here is going to be 0. Because shear strain gamma is a function of the distance from the center, if we're right at the center of the cross section, it's going to be equal to 0. Likewise, the maximum shear strain is going to occur the largest distance away from the center at the radius. And we're always going to deal with circular cross sections, so the radius is going to be the largest possible value for rho that we have, and that's where the maximum shear strain is going to occur. And it's a linear relationship between, so if we were to map out the shear strain at this point at the, I'll draw an arrow because it'll be going up potentially. If this is the value or the magnitude of the shear strain at the outside, we have a linear relationship where it starts out at 0 at the center and linearly increases until it gets to the maximum at the outside of the cross section. So that's important. We know what the behavior now of the shear strain is, 0 at the center, maximum at the outside, and we're going to use that to try to figure out, well, what does the shear stress do? Because we're going to assume a linear elastic relationship that Hooke's law applies, the shear stress is going to follow a similar distribution. Because shear stress is just proportional to shear strain if Hooke's law applies, we get the same exact shape of a graph, but instead of starting out at 0 and going to gamma, or the maximum gamma, it's going to start at 0 and go to the maximum shear stress. So that's kind of our Hooke's law step. If it applies, and we're looking at the same cross section, the shear stress will go from 0 to some maximum value. Well, let's call it tau max at the outside of the cross section. All right, but that's not all. That's not the whole story, because the distribution of the shear stress is important, but we also want to know, well, what is the value of the maximum shear stress? And we know that's going to be caused by the torque, and so we still need to do another step to be able to figure out, well, what value of maximum stress do I need out here in order to completely counteract the torque being applied to the section? That's kind of the next step of the analysis. One thing I want to point out here as well too is that if we had, let's say we had a torque going counterclockwise on this member, the direction of the shear stress is always going to be in the direction of the torque as well. So if this is the torque and I was looking at a point at the very top of this section, the shear stress would be going in that direction. If I was at the bottom of the cross section, it would be going to the right, because that tends to cause a counterclockwise rotation, which is the same direction as the applied torque. And you'll see that in some other examples here as well too. Okay, so we've already said that the shear strain varies linearly from the center of the cross section out to the radius, and so you can just interpolate for any point in between. But now we really want to figure out, well, how do I go from the shear strain to the shear stress, and how do I, or what's the relationship between those two? And then the bigger question is going to be, well, if I know what my internal torque is, how can I then calculate what my shear stress is, and specifically the maximum shear stress? So first thing, relationship between shear strain and shear stress. We already talked about that. That's Hooke's law. And now we need to figure out, well, if I know what the internal torque is just based off of statics, what is the internal shear stress going to be at any given point on the cross section. All right, so and this is worked out as well too in a separate video in a little bit more detail. So we're assuming that Hooke's law applies, and so we know that the shear stress is going to vary linearly from the center of the cross section to the outside. That's what you see in this photo right here. We have our externally applied torque, and it is inducing a shear stress at any given location. The direction of that shear stress is going to be causing the same rotation as the torque itself. So the torque here you see is going counterclockwise. You can use the right-hand rule for that. The torque arrow is pointed out of the page. That means that our fingers are curling on our right hand in the direction of the actual rotation. So counterclockwise torque, that means that each of the shear stresses are causing a counterclockwise rotation about the centroid of the cross section. And the intensity of that shear stress varies. It's 0 at the center, and it's its maximum value at the outside, just like the shear strain. And that's going to be important. Each of these shear stresses are acting on a small differential area. So each of these are acting on some little differential area. And so we can actually turn each of these basically into an individual differential force. So if instead of just looking at the shear stress, I could map out, say, the shear force acting at each individual differential area, and that force is simply going to be equal to the shear stress at that point times that differential area. And so that's going to be important because each shear stress basically causes a force on that little differential area, and that force is also going to be causing a moment about the centroid. And that moment is calculated as the force times whatever its distance from the centroid is. So the distance from the centroid is kind of doubly important. The first reason it's important is that the further away from the center of the cross section you are, the larger the shear stress is. So it increases the intensity of the shear stress, and the farther you are away is also important because it gives you a bigger moment arm. And so all of these forces caused by these shear stresses times their respective distance from the cross section center, all of those added up, all those little differential moments added up, have to equal the internal torque on that cross section. Right? This internal torque, in other words, is causing shear stresses on each little differential area, and each of those little differential areas have a force associated with it and a distance from the centroid, and all of those forces times the distance are little moments. All those moments added up for the entire cross section is what's caused by that torque. And that's basically what this slide is saying right here. The force at any given point is equal to the shear stress at that point times the differential area that it's acting on, differentially small. And the torque caused by any of those little differential areas is equal to the force at that point times the distance to the centroid, which is rho. And that tells us we can basically start to integrate all of those areas together, and we end up with the maximum shear stress is equal to the internal torque acting on the cross section T times the distance to the centroid from the extreme fiber, which is just the radius, divided by this integral right here, the integral over the area of rho squared dA. So rho is simply the distance of any point from the centroid, and dA is just that small little differential area the shear stress is acting on. And here rho is squared because I told you the distance from the centroid is doubly important. It's important first because the further you are away from the center, the larger the stress is, and the further you are away from the center, the bigger your moment arm to cause a torque about the center is. Now that integral in the denominator, we don't need to calculate that every single time using calculus. For a circle and for a pipe, a circle with a hollow in it, we have that just tabulated, but we call it J, which is called the polar moment of inertia. But you don't need to use the integral form to calculate it every time. We just have a basic formula for it that we're only going to be using circles and pipes in strength of materials, so you only need to remember really just one, maybe two equations. Okay, so our fundamental formula is that the maximum shear stress which is on the outside of the cross section equals the internal torque, which is a moment, times the radius c, divided by that polar moment of inertia. But we know that the shear stress varies from 0 at the center to the maximum value at the outside surface, and so we can also interpolate for any point in between. And so the better equation to use is that the shear stress at any given point is equal to the internal torque T times the distance from the centroid, which is rho, and it could be 0 all the way up to the radius, any point in between, divided by the polar moment of inertia. That's the better equation to use. And so if we were looking at our loading table that we've been talking about before, we can start filling in the torsional moment material now, which is chapter 5. And what we can see is that an internal torque is not going to cause any normal stress on the cross section. And so torsional moment acting on a cross section only causes a shear stress. Right? And the shear stress at any given point is equal to T times rho divided by J. And so rho is a location-specific property. It depends on where you are on the cross-section. You could be at the middle, you could be at the edge, you could be anywhere in between, and rho might change depending on where you are. And so I want to write down here just a note, rho equals the distance to, I'll say the point of interest, I'll say POI, from the centroid of the cross-section. So that could change. Unlike N over A for axial members, where the normal stress is the same at the edge as it is at the center, as the same as any other place, for torsional members, the shear stress will vary linearly with the distance you are from the centroid. Very important to keep in mind. Now, the sectional property, the value in that equation for shear stress, it doesn't change, is J. J is the polar moment of inertia, and we haven't got that calculation yet, but we're going to want to put it right here when we do, which is going to be in just a second. Okay, so that's this next slide right here. We know how to get the internal torque. This is statics, free body diagram, section cuts, just like an axial member. We'll go over an example. And the distance from the centroid is pretty easy. It just depends on what point you're looking at, what point of interest you have. Just measure the distance from the centroid. The polar moment of inertia is kind of like the area. It doesn't change regardless of what point you're looking at on the cross-section. And that integral that we looked at before in the denominator, for a circle or for a tubular shaft, it's really easy to calculate. It's simply equal to pi divided by 2 times the radius to the 4th for a solid shaft. For a tubular shaft, you simply take the radius of the outside, you take it to the 4th power, and you subtract the radius to the inside to the 4th power. Now a really common mistake, I would say J does not equal pi over 2 times C naught minus Ci, that quantity to the 4th. That's a really common mistake, and I'll just say common mistake. Just an easy algebra mistake to make. Make sure that you follow the order of operations properly for this equation. All right, so the units for this is not going to be like area. Here it's actually distance to the 4th power. So this would be like inches to the 4th or meters to the 4th. And this is basically, this quantity, this polar moment of inertia is basically telling us, based solely on the geometry of the cross-section, how effective is it at distributing out the shear stress caused by the torque. The larger the value, the lower the torques are potentially going to be. Okay, so the way this works, if we're just trying to calculate the shear stress in a tube or in a shaft, a circular tube or a circular shaft, we need to calculate it based off this formula T rho over J. So we need T, we need rho, and we need J. Statics is what we need to do to calculate T. That's just the internal torque, section cuts, free body diagram, equilibrium equations to calculate T. Then you'll need to calculate the section property J. That's a really easy equation. Another easy mistake to make there is that it's the radius to the 4th. Oftentimes people will put in the diameter, which is an easy mistake to make as well too. And then you can calculate the stress at any given point. Once you have T and you have J, any given point will have a specific value for rho, and so you can calculate it at the outside, you can calculate it at any intermediate point. The shear stress in the middle is always going to be 0, so that doesn't really need a calculation, but that's really all that you need to calculate the shear stress at a given point. All right, so this example, or something like it, is provided online as well too. I don't think it's the exact same example, but it's pretty similar. Here it's asking you to find tau max. And so one thing about shear stresses that's a bit different than normal stresses is that usually the sign of the shear stress is not as important. So if it asks you for the maximum shear stress, it usually means the largest magnitude of shear stress. So just keep that in mind. If you're not sure if it's asking for one or for the other, just report both. Report the largest magnitude of a negative shear stress and the largest magnitude of a positive shear stress. You kind of cover your bases that way. So one thing I do want to talk about here, even though we're not going to go through this problem completely because there's another example on YouTube, is the way to do the statics on this. If you didn't take statics with me, I think the easiest way to break this down and make it manageable is to use double-headed vectors to represent moments. And that way you can break this down into a two-dimensional problem and treat it identical to an axial member problem with normal force diagrams. So what I mean here is you need to use the right-hand rule and then transfer all of these torques onto a two-dimensional plot. And so here I'm going to redraw just the shaft itself, and we have A, B, C, and D. So I'll draw a point for each of those right there. Here the distances don't matter because it's not asking us about a angle of twist. It's not asking us or giving us a distributed load. But here, this is a two-dimensional free body diagram. Really try to avoid these isometric three-dimensional views when you could just as easily draw it in 2 dimensions, because I think that, especially drawing on paper without the benefit of a lot of time and CAD, is that a rotation can start to look like 2 different directions potentially. Okay, so changing these rotations, these torques, into a two-dimensional double-headed vector is just the right-hand rule is all that you got to use here. So here the right-hand rule simply states that if you take the right hand and you curl your fingers in the direction of the rotation, your thumb will be pointed in the direction of the sense of that vector. So the thumb is going to be the direction that we actually draw our arrow in. So here the torque at A, if I were to take my right hand and I were to rotate it in the direction of that 250 Newton meter torque, my thumb is pointed up and to the left. Whereas here at B, to get my hand to rotate in the direction of the torque at B, I've got to turn it around, rotate it like this, and then my thumb is pointed down and to the right. Okay, so A was pointed to the left, which means that I will draw a vector with 2 heads to clearly state that it's a vector, that it's a moment, and that's going to be my 250 Newton meter moment. At B, we said it's the opposite direction, a 2-headed vector in the other direction, 75 Newton meters. The 325 Newton meters is pointed to the right as well, 325 Newton meters. And then finally, the 150 Newton meters, the sense using the right-hand rule will be pointed to the left. So left, 150 Newton meters. So at this point, I have a free body diagram in 2 dimensions, and the sense of each of these moment vectors is pretty clear. I use the right-hand rule to do that, and now if these weren't 2-headed vectors and if the units weren't shown here, it would look exactly like a normal force diagram, which is not really a coincidence, and it makes our life quite a bit easier. So here, if this is my free body diagram, let's just do 1 or 2 quick discussions here. Let's just check and make sure this is in static equilibrium. So all that I would need to do to check this is in static equilibrium is sum the moments about the x-axis. So here we're not talking about forces anymore, we're talking about moments. So here if I summed the moments about the x-axis equal to 0, I will draw my coordinate system on the left-hand side. Any vectors pointed to the right are plus based off that xy coordinate system I put up there. Any moment vectors pointing to the left are going to be minus. And so I get minus 250 Newton meters plus 75 Newton meters plus 325 Newton meters minus 150 Newton meters. That does equal 0. All right, 400 minus 400, basically. So I'm treating it almost identical to an axial member when I'm calculating the internal normal forces. The only difference is that here I'm doing moments, but the arrows are pointed in the same direction, parallel to the longitudinal axis, and I think this will make your life quite a bit easier. Now, when it comes to the internal torques, it's the same exact rules as for an axial member as well, too. That means if I were to, let's say, make a section cut because I want to calculate, let's say, the torque between A and B, I'll make a section cut between A and B, and I will make a new free body diagram. So if we were looking at just member AB, I make that section cut. Let's keep everything to the left because it's easier, but I read the same answer either way. So I would keep everything to the left. Here's my section cut. This is point A. Now my internal torque, it follows the same sign convention as an internal normal force in the sense that the assumed direction of the internal torque is always away, pointed away from the section cut. So here, the section cut and the remainder of the member is to the left, so my internal torque is pointed away. And so my internal torque, AB, looks like this, and I still need to draw my externally applied torques as well. This is 250 Newton meters. So the same thing as before, I just sum the moments about the x-axis equal to 0, and I get minus 250 Newton meters plus torque AB. That means that torque AB equals positive 250 Newton meters. You can do that for the other section cuts as well too. And keep in mind, if I made that section cut between A and B and I kept everything to the right of the section cut, I would get the same exact answer if I follow the same sign convention, which means if I kept everything to the right of that section cut, here's my section cut, my assumed direction for the internal torque would be away from the section cut, which means to the left here. So my internal torque, AB, is now going in that direction. And the externally applied torques, I have 75 and 325. And I believe I have 150. Going to the left, if you run the statics, 75 plus 325 minus 150 is going to be positive 250. You get the same exact result. Okay, so for a problem like this, calculating that torque is kind of step number one, calculating the internal torques. And what might be helpful is to draw an internal torque diagram. So for this system here, my internal torque diagram is going to go up to 250 at point A. At point B, it's going to drop down 75. So it'll go from positive 250 to positive 175. Then it's going to drop down. It's going to drop down 325 Newton meters to negative 150 at point C, and then it'll jump back up at point D to 0. All right, so here's my internal torque diagram, and that would be the best ending point for the first step where you're trying to get the internal torque. Now, step number 2 is that we need to calculate the section property, J. J is easy for this. It's a constant cross-sectional shaft, and so that's pi over 2 times c to the 4th. Now for this problem, we're given the diameter, so make sure that you change that to 25 millimeter radius and then plug it into this equation. Now with this problem, all of the cross-sections are the same. They don't change. And so if we're looking for the maximum shear stress, really the only thing that could affect where the maximum is the torque, because J doesn't change whether we're in section A, B, B, C, or C, D, but the torque does change. And so when we calculate tau max, it's going to be T max times c, which is the radius, divided by j. Now you could imagine if the polar moment of inertia j in these sections was different, we might need to check all three sections, but here, because the only thing that changes is the torque, the largest magnitude of shear stress is going to occur in segment AB because that has the largest magnitude of torque. All right, so here this is going to be section AB will control for the maximum magnitude of shear stress, and we would just plug in those values, 250 times the radius, which is 25 millimeters, divided by the polar moment of inertia. Be careful with units as well too. It might be helpful to change everything to newtons and meters and not work in millimeters. Just make sure that you're dimensionally homogeneous when you get to the answer for that last calculation. All right, a couple other things to mention as well too. So a common question might be if, say we have a maximum shear stress or an allowable shear stress for a shaft, what is the minimum shaft diameter? That's a really easy question to answer if you have a solid shaft, because the polar moment of inertia of the shaft is just based off of the radius. So there's going to be a single answer to a question like that. Maximum allowable stress, and then the question would ask, what is the minimum solid shaft diameter or radius? That's a single, unique solution. Now when we have a tubular shaft, the polar moment of inertia is based off both the outside dimension and the inside dimension. When I say dimension, I mean radius or diameter. So in that case, if they ask you for the minimum dimensions, that's kind of tricky because you would need to pick either the outside radius or the inside radius first, set it, and then solve for the other ones. There's not a single unique solution for that. Oftentimes we'll base, if we had a question like that, we would look at a table of available pipe or tube sizes and we'd say, well, I see for a 6-inch outer diameter there's multiple different thicknesses, so you might set the outer diameter to 6 inches and see what the minimum thickness or the minimum inner radius would be, then choose your pipe that way. So you'd kind of base it off what available sizes are out there. Okay, so that's the first part of torsion. Now the second part, just like with axial members, we first looked at the stress component, and now we're going to look at the deformation component. So with an axial member, we talked about the change in length. Here, the deformation for a torsional shaft is the angle of twist of one point or one cross section relative to another. And you're going to see a lot of similarities here for angle of twist. And again, the derivation is fully worked out on YouTube, so we're just going to go through it very briefly here. But our goal here is to be able to go from the internal torque combined with things like geometric properties and material properties, but we want to go from the internal torque to the angle of twist, which is phi. And so the way that we do that, we first start out with our definition of shear strain. We know that shear strain is related to the angle of twist. We had that relationship up here. We looked at this relationship before, but if I rearrange it, I can rearrange it in terms of d phi, the differential angle of twist of two adjacent sections, is equal to the shear strain times dx over rho. But based off Hooke's law, remember Hooke's law applies to shear stress and shear strain just like it applies to normal stress and normal strain. And so I can put in the definition that the shear stress at any given point is equal to the internal torque, which could be a function of x. The internal torque might vary, it might not be constant, divided by the polar moment of inertia j. And here that's also shown as x, a function of x, because that we might have a non-prismatic shaft. And with a little bit of rearranging, we get to the point that the angle of twist is equal to the integral over the length of the internal torque as a function of x over the polar moment of inertia as a function of x times the modulus of rigidity, the shear modulus g. It looks very similar to the axial deformation equation. We'll look at the similarities here in a second. Now we like to simplify this because we don't like doing integrals if we don't have to. And so if you have a constant internal torque and you have a constant polar moment of inertia, then you can simplify it down to that simple ratio TL over JG. And so that only applies if you have both a constant torque and a constant. This has cross-sectional area, but technically here, let's just say polar moment of inertia, because that's really what matters, not the area. All right, so if you have multiple regions of constant torque or multiple regions of constant polar moment of inertia, say a compound shaft where over here it's 2 inches in diameter, here it's 1 inch, here it's half an inch, or maybe over here it's 100 Newton meters, here it's 50, here it's 400. If it's a constant T and a constant J over that entire segment, you can just add together all the results, treat each like an individual shaft, just like we did for the axial members in their deformation. Just like I said when we were looking at the internal torque, the assumed torque in a two-dimensional vector is pointed away from the section cut. If you use the right-hand rule, another way to think about that is if you're looking at the cross-section itself, if I was standing here and I was looking at the cross-section, that means the torque is going counterclockwise. Same thing, if I was standing here and I was looking at this other cross-section cut, the assumed direction of torque is going counterclockwise. The angle of twist goes in the same direction and it follows the same sign convention. So a positive phi, a positive angle of twist, means that it's going clockwise as you're looking at the cross-section cut itself. Okay, looks like a little bit of the words got cut off here, but it's essentially what I just said is covering that same material. Here's another example of the sign convention that we were talking about before. There's a couple of examples in your book as well too, but section cuts, I strongly recommend you change everything into two-dimensional double-headed vectors instead of trying to do it in a three-dimensional type view. So you could practice with something like this, and I have a video of this as well too, of changing this from the isometric kind of curved arrow into a planar double-headed vector to represent a moment. It's going to make your life a lot easier. Okay, so like I mentioned before, this is very similar to axial members in Chapter 4, in the sense that when we look at the torque, the general formula for the angle of twist due to a torque has an integral over the entire length. That's the same as an axial load. It has a loading parameter, like an internal load. Here it says P, but I want to change that to N. Let's say that's N. Internal normal force. Forgot to change that. Right, but both have a loading parameter, that an internal resultant that could change over the length of the member. Torque, internal normal force, is just the loading or internal resultant part of the equation. Both also have some sort of cross-sectional property. So here we have the polar moment of inertia J that could change across the length. We also have a geometric cross-sectional property here. For axial members, the area, that could be a function of x as well too. And then something related to material stiffness as well. For torsional members, that's the modulus of rigidity, also known as a shear modulus. For axial members, that's the modulus of elasticity. So similar format, the calculation ends up being very similar. The biggest difference is that the units are different for torque and for axial members, but that all works itself out. The final answer you'll get for phi will be in units of radians. It's unitless, but you still want to write RAD as the units. By default, unless a problem asks you otherwise, always report the answer in radians. Don't change it to degrees unless it asks you to. Okay, so this angle of twist example is worked out separately in a different YouTube video that you can take a look at. But here you see that we'll have 3 different segments. All of these have the same diameter, so they'll have the same polar moment of inertia. And all are made out of A36 steel, so they have the same modulus of rigidity, which you would just look up in the back of your textbook. The only difference here is that we're going to have 3 different regions of different torques. So AC, CD, and DB will all have different torques, and so the equation I'll need to use for this will be the summation of TL over JG. I'll have 3 different terms, one for section AC, one for section CD, and one for section DB. All right, likewise, so the previous example we did the arithmetic sum, which is nice because then you're just doing TL over JG. But if we have a shaft that you have to use the integral form for, it could be something like this. So one way that something would vary would be the polar moment of inertia might vary. And that's what's happening here. The radius is changing from point A to point B. So we need to define the radius as a function of x. And then we need to plug that into our polar moment of inertia equation. And then we'll need to integrate it over the length. The other thing that we could have done, instead of having a single torque, I could have had a distributed torque acting on this, in which case the internal torque would have been non-constant, would have been a function of x. We would need to integrate that. So here, we're going to say that phi equals the integral of t of x dx over j of x g, integral from 0 to L. For this specific example, the internal torque is going to be constant. G is always going to be constant. So I can rewrite this as equal to t over g times the integral from 0 to L of dx over j of x. All right, so a little bit of integration, nothing too difficult here. The example is fully worked out on YouTube. All right, so everything we've done so far is pretty similar to axial members, at least in terms of angle of twist. And just like axial members, we can also now deal with statically indeterminate torsional members, which means that statics alone is not enough to determine all of the internal torques acting on the shaft. And we get to use the exact same steps as we did for axial members. You can choose to do the stiffness and displacement method, where you do equilibrium first. You find out you don't have enough equations to solve for all the internal torques or the reaction torques. Then you use compatibility to say something about the relative angle of twist of the two different members. So if you had, let's say, a shaft like this, it's fixed on one side, fixed on the other, and we had some externally applied torque, let's just call it T sub 1, applied somewhere in between the two supports, you know that if this first segment is AB and the second segment is BC, you know the angle of twist of member AB has to be counteracted completely by the angle of twist of member BC, because the overall angle of twist from one support to the other, the overall angle of twist is 0. And that equals the angle of twist of member AB plus the angle of twist of member BC. So let's say member AB, due to this torque, rotates 0.1 radians. That means that member BC has to rotate negative 0.1 radians to cancel it out. That's the fundamental idea of compatibility. We're just applying it to torques here instead of applying it, sorry, that's a torque, so that should be have two heads on that arrow. We're just applying it to torques instead of applying it to deflected distances. Once we have those two simultaneous equations, one from equilibrium relating to the torques, one from compatibility relating to the torques, then we can combine them, solve them simultaneously, and get the answer for the torques. There's a fully worked out solution that kind of walks through this methodology as well too. And I would point out that you can also use the force flexibility method if you wanted to. You could instead break this up into two different shafts. You could also say that it's equal to two different shafts. I took away the support at the right-hand side. In the first one, I would apply the torque, and then I would keep track of how much angle of twist is applied, or it results at the end, where I took away the support. And then we would also apply a reaction torque at the far right-hand side at C, and then we would keep track of how much angle of twist would be caused by that reaction. And we know the angle of twist from the first case up above plus the angle of twist of the second case down below has to be equal to 0, and that will give us enough information to solve for the unknown reaction torque. All right, so here's an example pretty much out of your book. Same thing that we've been talking about before. If you're using stiffness and displacement method, statics will show us that it's indeterminate, that the external torque and the internal torques, we know that they're all related to each other, but we don't know the actual value of the torque at A and then the torque at B. So then we need to figure out, well, what's the compatibility here? And just like we said, the overall rotation from one end of the shaft to the other has to be equal to 0, and therefore the angle of twist of each of the segments has to cancel each other out. And then once you solve those simultaneously, you get that the torque at A is equal to the external torque times the ratio of length BC divided by the total length, and similar result for the torque at B. Now this is almost identical to the indeterminate axial member that we went through in lecture on Tuesday. So here's a fully worked out problem that's up on YouTube as well too. Here we have two externally applied torques, and you can use either method, stiffness displacement or force flexibility, to solve this. Just change all of these curved arrows into two-dimensional double-headed vectors, and then treat it just like an axial member problem. You'll get the same analysis, same steps, and it's relatively straightforward. I did post the solutions to this one as well too. This is about as difficult as it gets. I don't have anything like this on the homework, but just keep in mind, here we have a statically indeterminate shaft. Member AB is going to have, the angle of twist of member AB is going to be difficult to calculate because it has a linearly varying distributed external torque, which means if it's linearly varying externally, then the internal torque is going to vary parabolically. So the internal torque will be based off a parabolic equation, which means that the angle of twist is going to be a polynomial to the third power to calculate it. So I have the fully worked out solution if you want to take a look. The other things that complicate this is that member AB has a different diameter than member BC. So if you want to look at a more rigorous example, I fully expect that once you're done with this class, you should have enough tools to tackle something like this, but I'm not going to saddle you with this additional work for the homework. So that's it for torque. Again, keep in mind that there are a lot of similarities with axially loaded members. Do yourself a favor, change everything into a two-dimensional shaft free body diagram. Draw your moments using double-headed vectors in 2 dimensions using the right-hand rule. And other than that, send me an email if you have any questions. I don't have office hours on Thursday this week, but I do have office hours on Monday, and the tutors have their regular office hours this week as well too. And take a look at those other videos that are posted up on YouTube.